at the intersection of science and innovation. The field of geoscience continues to evolve rapidly, driven by breakthroughs in data analysis, remote sensing, artificial intelligence, machine learning, and sustainable exploration practices. These technologies are not only transforming how we understand the Earth, but also how we respond to the pressing challenges of our time, from climate change to resource management. So today's meeting is a platform to share knowledge, and I want to encourage all of us to engage actively, challenge ideas, and explore new perspectives. So let this gathering spark meaningful dialogue and innovation. Let's make this meeting a productive one, enlightening and forward-looking meeting. Once again, I welcome you all to this very important meeting. Thank you all. So I would like to hand you over to the anchor speaker. Okay, no, not really, but I think we have a safety briefing from Mrs. Folashade Oladipo. I don't know if she's around. Ms. Folashade.
She's around.
She's around. Okay. Please, over to you, Mrs. Folashade Oladipo, for your safety moment.
Thank you so much, Dr. Eunice. And good afternoon, everyone on the call, all the leaders, all the members of the leadership team, and the executive of NAPI, the Abuja. Thank you for having me. Dr. Eunice, I don't know, do you have my slide? Are you able to read it up for me, please?
Oh, not really, no.
Okay, could just try to share from here. I would have tested it ahead, but I've just been promoted to be able to share things.
If you have it, you can share it.
Yeah, so I'm just going to do that now. Thank you.
Okay. Okay, fine, you can see it.
All right. Dr. Eunice, I'm just going to check with you. Are you going to do the intro or I just go on?
But just go on.
All right,
okay,
thanks.
Hold on, let me just see if I could just get it right now. Okay. Okay, please just go on.
Okay, good. All right, thanks. I have very few minutes to spend with you, so I'll just dive right in. And I have some interesting statistics to present to you. As you can see on the screen, you know, reports have it that 50% of CEOs leave their jobs as executive leaders within 3 years owing to burnout. And 90% of the members of C-suite actually have sleep issues because they're afraid of failure. And last year alone, 19 CEOs were lost while in active duty. They died while, or passed away, let me use that word, while they were in office. And let's face it, these statistics are bad. And I don't want to be dramatic, but I'm starting to think that the role of a leader is starting to sound to me like that of an extreme sport, because when I look at these statistics, don't you think so? And honestly, if this job, this role, came with a helmet and a seat belt, I won't be surprised, because at this rate, you and I would need it. Now, I said these statistics are bad, and I'm here to invite you. I want to reverse the statistics. I'm also here to invite you to join me in reversing that statistics, because if you're a leader, if you're a member of the C-suite, if you're a manager, an elite professional, I see you. I understand you. I know you are doing everything right based on what you can see. You're pushing, you're grinding, you're showing up. But somehow, at times, you just still don't feel enough. The board is not yet seeing your full value. Your teams are not running as fast as you want them to. And at times, this feels heavy. Your decisions are not landing as bold, as big, and as brilliantly as you've envisioned. And then there's the fear. Have I hit my limit? Am I doing the right things? Am I taking the right steps? Are my decisions landing correctly? And then you tell yourself, well, this pressure is going to ease off soon. Things are going to settle. Once I get to the next level, that next milestone, that next win, things are going to be better. But you and I know that goalpost shifts. Expectations never stop. And you know the worst part of it is that everybody thinks you figured it out. When you walk into the room, what they see is success. They don't see the exhaustion, the self-doubt, or the fear. They don't know how hard it is for you to turn off. They don't know how hard it is for you to be present with your family when you're stuck in strategy mode. They don't know how hard it is for you to carve out time for yourself when every minute of the day you are solving problems for everyone. They don't know how hard it is for you to breathe. But I see you. I see the pressure, I see the weight, I see the tight ropes because I've been there. I've been exactly where you are, and I'm still there, and I understand it. And it's not because you're not doing enough, not working hard enough, or you lack the skills or the strategy or the drive, but it's just that there's something right in here in your mindset that is holding you back. And this is what I've learned from working with executives, senior managers, elite professionals. It's a proven statement, a proven conclusion that ambitious leaders, you don't have a career or a business advancement issue. The issue is with a growth mindset. And I know you're going to be like, what? Mindset? Really? Folashade, what is that? Yeah, I know. It's a blind spot. You can't see it. It's a hidden pattern. It's just running the show in the background. But I know, based on my work with the tribe, and the question I want to ask you, if you think this is fluff, is to ask you how many times you have doubled down on effort, you've refined your strategy to the best, you've put in hours, and at the end, you're still not getting ahead as much as you want to. You kind of feel that you're hitting an invisible wall. That's a blind spot. And with all of this effort put in, you're still there because the issue is not external. And this is what I know from working with the group of executives and leaders, is that you've been solving the wrong problem. Because what you've been dealing with has been external. But what we have to look at, where the real hazard is in here. And that's what we have to deal with. So I want to invite all the brilliant leaders in the room to join me to reverse the statistics. And if a part of you, or if this is speaking to a part of you, and that part of you is saying, yes, we need to reverse the statistics, I want to ask you to please join me in aligning your inner advantage to address the blind spot, to address what success is costing you and I behind closed doors, because safety starts from the mind and flows outwards through our action. So this is your moment, my moment, the safety moment. Thank you.
Thank you so much, Folashade, for that beautiful presentation, which was wonderful. And safety starts from within, indeed. Thank you so much. Well, I'm going to be moving to the next agenda, which is the introduction of the chairman, and that will be done by no other person than our coordinator for the Abuja chapter, Dr. Eunice Ajayi. Please, you have the floor now to introduce our chairman of the day. Thank you so much.
Thank you, Boson. Well, it's my pleasure to introduce our chairman for today's session, a respected leader in the global energy industry, and a dedicated member of the Nigerian Association of Petroleum Explorationists, Mr. Akinola Idowu. Mr. Akinola Idowu is a seasoned energy executive and technology strategist with over 30 years of experience across oil and gas and renewable energy development. He spent 21 impactful years with Chevron, where he led breakthrough initiatives in subsurface innovation and asset optimization. Today, he serves as the managing director of Stellar Solve Energy Nigeria Limited, a firm committed to advancing sustainable energy solutions in the sub-Saharan Africa. He's also a director at ENREC Nigeria Limited, supporting energy resilience, responsible resource development, and clean energy across the region. In addition, he's a principal consultant at Stellar Geoscience LLC, based in Houston, Texas, a leading advisory firm focused on global energy transition, subsurface intelligence, and renewable energy strategy. Mr. Idowu is a certified ESG strategist and an advocate for responsible energy development. Mr. Idowu is a proud NAPE member. He remains actively engaged in the leading professional associations, including AAPG, SPE, and HGS, and he continues to mentor the next generations of geoscientists. Please join me in welcoming our chairman for today's webinar, Mr. Akinola Idowu. Mr. Akinola, you have the floor. I would like to introduce the speaker, the guest speaker, and also do the citation.
Thank you so much,
Welcome.
Dr. Eunice Ajayi. It's an honor to actually be the chairman of today's event. This is the season where we do know that there's a lot of new technology that enables us to be able to do some of the things that I think Folashade mentioned, and be able to do it from a position of rest. We're enabled to actually not to be worried in many ways people used to be worried in the past, and that's the beauty of technology. And again, it's also very important that we equip ourselves, and that's why we're having this session, equip ourselves with these tools by leveraging and having people like Mr. Roden, who is going to be speaking to us about the trends in geoscience technology today and in near future. So introducing him, it's an honor for me to actually introduce him. It's my absolute pleasure to welcome every one of us to this event. Today is what you could consider a forward-looking event to what's going to be tomorrow, the future is going to be. We can start from now and start stepping into the future. And that's the theme for today. Today's session, stepping into the future of geoscience. And it's an urgent call to action for all of us in the community, both in Nigeria and across Africa, because I'm aware there are people beyond Nigeria that are here from Ghana and from Senegal that are joining us today, thanks to technology as well, to be able to do that. And to lead us today into the future is someone uniquely qualified to do so. He's our guest speaker. His name is Mr. Roden. He's a world-renowned geoscientist, seismic interpreter. Is an educator whose work is shaping the future of AI power geoscience worldwide. He's, and a testament to this, he has over 100 publications over his career. He has over 50 years in the industry. Mr. Rocky will be speaking again, and like I said, trends, we'll be speaking on trends in geoscience technology today and in the near future. His presentation will be exploring how artificial intelligence, machine learning, full waveform inversion, FWI, large language models, and even quantum computing are transforming workflows in stratigraphy, fault and fracture detection, phase shift prediction, and reservoir characterization. So I had the privilege of meeting Mr. Rocky in 2019 through Geophysical Insight, a company here in Houston. While he was driving, he was at the forefront of driving AI seismic interpretation tool like Paradise. Since then, I gained invaluable insights from him, and I've always looked for opportunity to have him a platform where he could share more of this to a larger audience. This is just, it's not just technology for me. It's about creating more value for Africa, for Nigeria, for all the countries here. And it's done by reducing dry hole risk, improving confidence in our field development decisions, and building local capacity for tomorrow's challenge. No resource should be stranded by the year 2030. That should be a goal for all our leaders. So ladies and gentlemen, please join me in welcoming our speaker, Mr. Rocky Roden. I'm going to read a citation of Mr. Rocky just before starts. So, like I said, Mr. Rocky Roden is a geophysicist. He has over 50 years of experience in oil and gas industry. He's the president and chief geophysicist of Rocky Ridge Resources Incorporated, a consulting firm he founded in 2003. Throughout his illustrious career, Rocky has held pivotal roles, including the chief geophysicist and director of applied technology at Repsol YPF, where he advised on exploration and development strategies across multiple continents. He has also been instrumental in advancing seismic interpretation technologies, serving as chief consulting geoscientist at Seismic Microtechnology, and contributing significantly to the development of machine learning applications in geoscience that at Geophysical Insight. Rocky's commitment to geoscience community is evident through his extensive authorship of over 100 technical publications and presentation, as well as leadership roles in professional societies such as SEG, AAPG, HGS, GSH, EAGE, and SIPES. He has also served as the chairman of the Leading Edge, the editorial board, further showcasing his dedication to advancing geophysical knowledge. Please join me in extending a warm welcome to Rocky Roden, a visionary leader and innovator in our field. Mr. Rocky, and just before I hand over, Mr. Rocky, is he here?
Yes, I'm here.
Yeah, I was just going to say, so yesterday we did chat, and there's going to be a surprise for everyone. At the end, we're going to be doing a giveaway, some kind of giveaway that you could only give online for those who stay to the end. So I'll encourage all of us to listen to the end, and then you'll be able to partake of the giveaway. Thank you. Over to you, Rocky.
Thank you, Akeem. And I want to thank the Abuja chapter of NAPE for allowing me to give this talk today. And I hope you get something out of it. I think that our whole world is changing, as it was discussed earlier, with AI and ML and these sorts of things that can be very confusing and can be very complicated. But really, if you boil it down to the basics, it's not. It's not that complicated. It's involved at times, but hopefully I can present what I see is happening and coming down the road as for geoscience technology. Okay, let's see if I can get my okay, can you see my screen?
Not yet.
Hey, do I need to do something to get the screen up?
Not the, maybe just try again.
Okay, let me get out of here and
Just share.
oh, share. There you go. I missed it.
Share at the bottom. Yeah.
Okay, it's coming up. It's up now. We can see your slides.
Okay. How's that?
Good.
You can see it.
Excellent.
It's okay.
Whoops. Lost it there for a second. There it is. Can you see that now?
Yes, we do. I do.
Okay.
See.
All righty.
You can see it.
Okay. Again, this is kind of a showing you some of the trends in geoscience technology today and in the future, and I hope you enjoy it, and I welcome any questions as we get to the end. All right. What I'd like to do is initially go over kind of a general understanding of artificial intelligence and machine learning. Those words are used a lot in our everyday life, and sometimes it's confusing exactly what it is. I'm going to go over that. And then I'm going to go over very specifically kind of where AI and ML have been used in geoscience in our industry. And I'm going to talk about full waveform inversion and the potential this has to change the way we not only acquire seismic data and process it. And the impact could be quite dramatic. And then talk about computer power, because this actually is something that advances all these technologies. And some things are happening that are quite exciting, and I'm going to go over that. So first, I'm going to go over this kind of a general understanding of the types of what is artificial intelligence and machine learning, and to get a better understanding of exactly what we're talking about when we say that. Now, this is a kind of a general graph showing the various sorts of categories of science, data science, and here we go. And artificial intelligence is the big umbrella under which all of the other sorts of applications related to machine learning are located. And this is any technique that enables computers to mimic human behavior. Now, really, most of the things we deal with are really machine learning. And it's a subdivision of artificial intelligence. And these are techniques that give computers the ability to learn without being explicitly programmed. And a subset of that are neural networks. These are interconnected nodes or neurons. This is where they have developed applications that mimic the human brain. Very interesting. And a subset of that is deep learning, which is no more than numerous layers of these neurons. And in fact, in today's world, if you have more than 2 or 3 layers, it's considered deep learning, because you hear that word used a lot. And then something that has taken the world by storm the last 3 years is, first of all, is generative AI. Now, generative AI has been around for a dozen years or more. And it's nothing more than it creates content based on user prompts and learns patterns from data. It generates original output. But it's a subset of that called large language models that have taken over the world in the last two or 3 years. And what this does is it is designed to understand and interpret human language. And these are the general categories of machine learning. And arguably, there's one more that I will discuss that is evolved on the scene here the last few years. But supervised learning is the most common type of machine learning. And what that relates to is I've got a bunch of data, and I know the answer to this set of data. So what I do is I go through and I develop a bunch of descriptors or labels that helps me build a model to give the answer that I know is the correct answer. And once I've built that model, I'll apply it to a different data set, hoping to find out and get that answer. This is the most common type of machine learning in the world, actually. Now, unsupervised learning is very, very different. It knows nothing about your data. And what it does is it goes through and it looks at the natural patterns and clusters in your data. Usually a lot of different data types are involved potentially in this unsupervised learning. Now, in today's world, semi-supervised is nothing more than a combination of supervised and unsupervised. And then reinforcement learning is where you actually learn from the mistakes with an agent to get the right answer. So really, supervised and unsupervised are the dominant applications used in the world, actually, but especially in geosciences. So I know that it's difficult to give a test to everybody over the line like this because you can't answer. But if you look at this screen, what is the answer where the question mark is? Well, hopefully you got 81. And the thing, well, how did you get that? Well, you looked at these numbers. You saw that if you squared each one of these numbers, you got the number to the right. So you build a model, you square the 9, you get the answer. And if you did that, then you have successfully accomplished supervised learning. That is the fundamental principles of what supervised learning is. It's the approach that is used. And there are really 2 types of supervised learning. One is regression and one is classification. Now, regression is nothing more than fitting a line to the trend in the data. And we've all done this. If you've ever done any AVO analysis, you have a linear regression line that computes the intercept and gradient. If you've ever done any sort of development drilling where you use a decision tree, these are the applications that are supervised learning. There are non-neural network approaches. So you have regression for the line fitting, and then you have classification, which is very similar to regression, except instead of looking at a line to the trend, you're actually separating by lines or planes the different information in your data. And you hear logistic regression, k-nearest neighbor, support vector machines, classification, and then very similar sorts of applications used for looking at the trends. Now, these applications that I've just described are traditional linear understandings and predefined statistical models. Neural networks are very different. You'll see that in just a minute when I explain that, but they are not these standard statistical approaches that have been around for a long time. Neural networks are very different. Here I have another test. Look at these 6 objects and tell me how many patterns or clusters can you identify? Let's look at that for a second. Well, hopefully you identify where there's shapes, round versus a box. There's fruit and non-fruit. There's colors, variations of colors. But if you were able to get any of these, then you've successfully accomplished unsupervised learning. You just looked at the data and identified the natural patterns or clusters in the data. That's all unsupervised learning is. Very straightforward. We basically have two types, clustering and dimensionality reduction. And all this dimensionality reduction means is if I've got a whole bunch of different types of data, how do I reduce that towards a workable data set? And typically we use things like principal component analysis to help do that. But this is really this unsupervised learning is in clustering. And what that is good for data exploration, anomaly detection, and data mining. That sounds a whole lot like us exploring for oil and gas, doesn't it? Exactly the approaches that it does. Probably the most common unsupervised neural network is self-organizing maps. And the reason that is used for in geology and geophysics is it has something called topology. And all that means is that all these neurons that find these patterns or clusters, it also tells you how similar they are to each other. And that's extremely important in geology. If you think about stratigraphy and the geological features, depositional environments we look at, they're somewhat related to each other, and that has a big impact in interpreting data using unsupervised methods. But why should we use neural networks? I've talked about that, and well, if you look at geoscience in general, of course, we've built what we know about geology. It's based on physical laws and principles that have been discovered over the centuries. And these features have space and time relationships, very multivariate, nonlinear trends, non-stationary characteristics, and often involve rare but significant events. So our geology can be quite complicated. And that's where neural networks come in. And it has advantages over some of those applications that I was showing you. There are predefined mathematical models in feature engineering. For example, it can learn very complex nonlinear relationships. That is very significant because geology quite often is not linear. Yet that's an assumption we make quite often. It can handle high dimensional data sets, which all that means is it can handle a lot of different types of data. Unstructured data. Yeah, a lot of people don't realize that most of the things in geology are not normally distributed or Gaussian distributed. They're usually something else. Neural networks can deal with that, and obviously complex problems. This kind of brings us next to large language models and how that fits in this overall scheme of things as it relates to machine learning. Basically about 2.5 years ago, large language models have revolutionized artificial intelligence and machine learning and natural language processing. It's achieved just unprecedented proficiency in understanding and generating human language. And it uses something called transformer architecture. And I'm going to show you what that means. It's not that complicated. But it learns patterns and structures of large data sets. In this case, it's looking at language. And it's for understanding it and producing coherent and contextually relevant text. And this transformer architecture incorporates something called self-supervised learning or self-attention. And I told you that there was maybe another sort of machine learning. Well, this is kind of what that is. And it kind of fits in between supervised and unsupervised learning. And I'll explain that to you in just a minute. But what's happened is that now this has evolved is back in 2017, Google initially developed this transformer technology. And I don't know if they didn't understand what they had, but a company called OpenAI took that technology, and over a period of about 5 to 6 years and about $500 million, they developed ChatGPT, this large language model that just everything went crazy after that. It had 100 million users after 2 months after it was introduced. And it was growing, and even NVIDIA, which makes GPUs, which are used for a lot of this machine learning, exploded, that company particularly, and it actually was the largest company in the world for a while because of that. However, in January of this year, DeepSeek came out. This came from the Chinese, and they did this in a much quicker time frame, and theoretically, it's supposed to be faster. Now, right now, today, there are a lot of patent lawsuits and a lot of issues going on. So we'll see how all of this evolves over the long term. But there's no question that large language models have changed the way we interact, and especially as it relates to machine learning and artificial intelligence. And I'll just go through this really quickly because it actually has a basis in a lot of geological applications that are being developed right now. If you're looking at a large language model, what it does is does something called tokenize. And all that does is it takes all of our words in language and converts them to numbers. We have to convert them to numbers somehow. And when we do, we also do something called embedding, which it puts it in vectors. And all that means is you've got all these words and a lot of syllables in these words that have numbers now, and there's kind of this multi-dimensional space where these vectors know where all this information is at. And then it does something called encoding, which says it knows where all those words and syllables are located. And this is where the self-learning comes in, the self-attention. And what it does is it learns the importance of each word, and then it develops the descriptors or labels that goes into supervised learning. You remember I told you earlier, for supervised learning, you have to have some sort of a label or descriptor. Well, it actually identifies its own labels. Absolutely phenomenal. Then it goes into deep learning. You have multi-layer supervised learning applications now. And then it calculates the probabilities of these words in the order that they need to be. And it does some back propagation and reinforcement learning to clean things up at the end. So this is what this transformer technology is. Quite ingenious, and has changed the way we look at things and actually interact. I won't go over this in detail, but this is a paper that just came out in Geophysics. And what they did is they used this transformer technology, but instead of using language, they used over 2.2 million seismic images from 192 seismic 3D volumes around the world. And they did this in an effort to determine seismic facies, geobodies, inversion, and denoising and interpolation in seismic processing. Just absolutely phenomenal sort of technology. And if you haven't looked in the February version of the Leading Edge, there's a whole section that's based on generative AI and LLM models in geology and geophysics. So it's coming. The evolution of this technology is coming as it relates to geology and geophysics. So now I'd like to talk about how this artificial intelligence and machine learning has been used in our industry and kind of where we are right now. There was a paper that came out last year in Geophysics, and what the authors did, Anjum et al., is they looked at all of the publications in the SEG and the EAGE from 2010 to 2021. And that is this blue line you see right here. Well, as you can see, nobody really used any machine learning in our industry until after 2016. And then it took off. Now, some of the other fields, when they looked at other databases, they were more accepting of machine learning and applying it than our industry is. And so this is when it took off after 2016. And they actually looked at not only the seismic processing, but interpretation. And what I'm showing you here are the results they got in looking at the applications of interpretation in these journals. And the number one application was fault detection. Number two was lithofacies classification. Number three was petrophysical and rock physics information. Now, what you see on the right is a graph that they put up, and across the bottom are the interpretation applications. But on the y-axis here, these are all of the machine learning applications to find these particular applications and interpretation. And what you see, what I've added here in yellow, those are neural network applications. And the ones that are underlined are unsupervised methods, and all the ones that are not underlined are supervised methods. Well, the first thing you notice when you look at this is CNN, which are convolutional neural networks. This is a deep learning, multi-layered, supervised learning. And it evolved out of image processing. It dominates everything. It certainly dominates fault detection, which is the highest application found in these journals. In lithophases, you actually have a little bit more of a spread in the different sorts of neural networks. SOM comes in here, which is an unsupervised method. And then in the petrophysical applications, it's a little bit more dispersed also. So this gives you an idea of kind of where we are at today. And a majority of these machine learning applications have been applied for very specific singular tasks. There's not a lot of integration of putting these together yet, at least from an interpretation standpoint. But remember, just because there's publication on it doesn't mean it's being used in our industry. Some of these are, most of these are not. I can tell you that in that I have the opportunity to review dozens of prospects and applications and technical evaluations every year from dozens and dozens of companies. And so I kind of see what's being used in the industry. It is starting to be used, but it's certainly not mainstream application yet. So full waveform inversion, how does that relate to seismic data, the acquisition of seismic data and the processing of seismic data and the implication of what's happening? For those of you who are not familiar, full waveform inversion actually was a nonlinear data feeding or optimization application that was kind of thought up back in the 80s. And what the idea was, we can use the whole seismic wave field to process our data, to look at the subsurface with our seismic information. It's an optimization problem. And what I mean is, you look at the difference between the measured data and a synthetic model, measure those differences and correct for them. And I'll show you how that works. And today, we use full waveform inversion is primarily for acoustic full waveform inversion that only accounts for compressional or P waves. Well, that's not exactly what the vision of what these initial authors had on what full waveform inversion is. So this is a very quick diagram showing you, this came from Dennis Vig, to show you what we're doing. It's not very difficult to understand, but it's quite involved in the amount of computational effort. If I have I've shot my seismic data, and I got my shot record sitting here, and somehow I compute a velocity model of some sort. And I have to I take that velocity model, whether I'm using tomographic methods, which is fundamentally the way we do it today, and migration velocities, and I actually do some finite different propagation or modeling. I come up with a model data set. I compare the real data with the model. I go over here and start using machine learning to see the misfit between the real data and the model. I look at all these misfits, and then I go through and use most of today, these machine learning applications are used in gradient-based optimizations. In other words, they see the differences, they modify those, filtering, weighting, and muting these different differences between the model and the real data. Then you go through and you go through model again with these improvements based on the gradient-based optimizations, make a new model, compare the differences, and you do this over and over, this optimizing process. And once you've done that, when you get what's called a global minimum on the misfit, there you've got the answer. Well, it sounds pretty straightforward, and it is straightforward to some degree, but the computational effort on this is tremendous. I'll give you an idea of what that is. So here's an example. This is a typical velocity field that we normally get with today's conventional processing methods. This is what the acoustic, remember, P-wave only, full waveform inversion velocity field. It looks like real geology. This is the step change that's going on right now. And here's an example. On the left, you're looking at, this is in Atlantis field in the Deepwater Gulf of Mexico. There's a conventional velocity field. Here, I've taken that velocity field and processed it like we normally do with the latest migration algorithms, RTM. You can see basically the imaging quality. Here, I've got the acoustic full waveform inversion velocities here. There, I've applied that same migration and processing algorithm, but I'm using these velocities. As you can see, I've improved the image. And I'm going to show you in a minute even an advancement over this. But, however, there are limitations to this acoustic full waveform inversion. There are mode conversions at the boundaries. The true phase and amplitude requires the physical phenomena of the wave propagation. It means all of it, not just the P waves. Cycle skipping in the model, illumination issues. True reservoir characterization requires the entire wave field. This is why elastic full waveform inversion is really where we're going. This is the direction that you'll see most of the processors involved in full waveform inversion are going. And this actually incorporates the entire wave field. It actually is doing what the initial definition of full waveform inversion was. So here's that very first example that I showed you, the conventional approach, acoustic full waveform inversion. Now here's the elastic full waveform inversion velocity. So I've done step changes and improved the imaging, as you can see here. But we've gone another step forward. Here's in the Caesar Tonga field, again in the Deepwater Gulf of Mexico subsalt. Here are the RTM with the initial velocities. This is conventional processing. Here is a typical migration with acoustic full waveform inversions. Here is the typical migration with the elastic full waveform inversion velocities. Here is the elastic full waveform inversion reflectivity. There is no conventional migration. This is 100% optimization. There is no reverse time migration. There is no Kirchhoff migration. It is purely an optimization process. And it absolutely gives you the best answer of everything. This is the direction we're going. This is where our industry is trying to go. But what is limiting us? Well, part of it is the acquisition, the type of data we're dealing with. We have to have low frequencies. We have to record our diving or turning waves. We have to have very, very long offsets. And typically we need to have full azimuth. Well, how do we do this? Well, one of the methods that has evolved in the acquisition end of it is ocean bottom nodes. And there's things called these sparse nodes acquisition where they literally have certain lines that go out 40 and 50 kilometers to record these deep diving waves and turning waves. And this absolutely these OBN receivers, which are multi-component, are placed on the seafloor. It's being done onshore too, but predominantly offshore now. And these autonomous ROV setting them on the seafloor. The technology is evolving and it's tremendous. To give you an idea of the impact of what's going on, this is a graph from Christian Johansson, the CEO of TGS. And he has the streamer acquisition. This is streamer acquisition from 2006 until today almost. And as you can see, in about 2012, 2013, we had about 60 crews shooting streamer seismic data. And then because of a series of market issues, companies going out of business, being bought by other companies, till today, we fundamentally only have 2 companies Shearwater and TGS, they shoot streamer data around the world. The consolidation has been pretty dramatic, down to only about a dozen crews. But as that has gone down, ocean bottom nodes have started to evolve, and the money being made on those is going through the ceiling. As you can see, this is a trend from 2000. And what you're looking at, the colors represent the parts of the world that ocean bottom node acquisition is being acquired. And it is dominated by BGP and TGS today. Again, a lot of interest in ocean bottom nodes and the evolution in our seismic industry. So that sounds so good and it sounds so great, and I've got some encouraging results. But what's the largest barrier to full waveform inversion? Computer power. Now, why is that? Well, let's put it this way. Dave Monk, in his distinguished lecture tour with the SEG, indicated that if I run full waveform inversion at 2 hertz, however long that takes to do it, if I process it at 64 hertz, it requires 1,000,000 times more computational effort. That's why you see a lot of these results related to specific frequencies, because to do it over the broadband, we just don't have the computational ability to do that today. And what we've seen is great advancements in the last 5 years going towards elastic full waveform inversion, but it's typically being used in some of the very largest fields in the world, especially in subsalt settings, but it's being applied in a lot of different places now. And what it requires is high performance computing or supercomputers. And our industry uses some of the largest supercomputers in the world. So how does that mean? How is this computer power going to affect us? And does it affect us? Well, here is a list of the top 5 fastest computers in the world. And this company called Top 500 measures the fastest computers in the world every year. And as of November of last year, the second fastest computer in the world was at Oak Ridge Laboratory in the United States. 1.353 exaflops. That's 10 to the 18th, which is a quintillion calculations per second. But the number 1 fastest computer in the world is at Lawrence Livermore, 1.742 exaflops. That's a lot of power. And one thing I want you to notice is it uses over 11 million CPUs and GPUs, or seismic processing chips. Absolutely phenomenal power that's being evolved with these supercomputers. In fact, they also looked at how they're being used. What's the application of these supercomputers? Well, energy, they didn't define exactly what energy is, but they do have geophysics down here as number 16. And I can tell you that application there is from Exxon. Exxon is number 16th in the applications in the world on using geophysics in their updated supercomputer system. So what are the sorts of things are evolving from a computer power standpoint? Well, one of the things, saying that we say the elephant in the room, or what's coming that nobody quite understand the impact, is quantum computers. In fact, many experts say that within a decade, quantum computers will fundamentally change how we do computations. In fact, they have quantum computers today who actually do work. They don't do anything in most cases better than our classical computers. So the question is, what is quantum computing? What does it mean? What's different between that and what we do today? Well, quantum computing is based on the laws of quantum mechanics. It is not based on our world of Newtonian things we see every day, Newtonian geophysics or physics. This is at the subatomic level. And so what different companies are doing is they're taking advantage of that, working at things at the subatomic level to build hardware for quantum computing. They're trying to leverage this. And the thing that what's different is classical computers use bits, as we know, 0 or 1. But quantum computers use qubits. It's a 0 or a 1 or a superposition of both. And so what does that mean? Well, what it does is it allows you to have multiple computation pass at the same time. So what does that mean? Well, for example, if all the doors in London were locked, except for one, how would you go about and try to figure out which is that one door that is not locked? Well, with our normal classical physics, you would quadrant off the different parts of London and you start opening these doors until systematically you ultimately find the door that's open. Well, in the subatomic world in quantum mechanics, it checks every door at the same time. That's the difference. It's a different world in the subatomic world of quantum mechanics. And there's different things called interference, there's entanglement. I won't go into that, but there's crazy things that sound science fiction, but are proven scientific facts. And the thing to remember about is quantum computers can store, if you take 500 qubits, that's similar to 2 to the 500th power normal bits. That gives you an idea of the magnitude of differences in the potential speeds we're talking about with quantum computing. So today there's intense competition from companies and governments around the world with all sorts of different sorts of quantum computing quantum computers being built, and not exactly sure who's leading yet. There's jumps in technology routinely being evolved with these computers, and who knows yet who's going to come out on top yet. We just don't know. So at my last slide, I want to give you an idea of just my possible interpretation workflow environment in the near future when a lot of these technologies have evolved. First of all, we have quantum computing that's sitting in the cloud, working at the speed magnitudes faster than anything we do today. That's where all our data is. That's where all our applications are at. It's all interfaced with a large language model interface. And it uses agents and it connects all these different applications, but they're all running at the speed of quantum computing. And it enables us to have machine learning automated workflows. We're not going to do one machine learning application at a time. We're going to start combining those in our workflow. There's no reason to do one at a time. And we're going to start combining different machine learning methods to get the best answer. And what this does, it allows us to do modeling beyond anything we can do today. Digital twins, software-related models and simulations. And ultimately, it'll get to the end goal, which is to be able to define reservoir properties and rock physics models directly from our data more accurately than anything we can do today. That's the end of my presentation. Thank you very much.
Thank you so much, Rocky. I mean, that was outstanding. It was really like drinking from a water hose, you know, a whole lot of excellent, you know, top-notch information that you're communicating to the region. I'm sure a whole lot of us have learned or have gotten new information. I mean, for me, personally, when you shared through, I think it was particularly the aspect where you talked about so generative AI, you know, in the leading edge. I'm surely going to go look at the February leading edge to be able to get to that. But in all, I actually think you've addressed, shown us what the future will look like, you know, in the next couple of years, where the seismic interpretation structural analysis, how we will be able to apply all this new technology to create value, in this, and be able to do things better than the manual methods that we do now, and we become augmented people in our jobs. The role of AI, ML, and stratigraphy and Fishy prediction to the power of all the way to what FWI for velocity modeling can do, and also the fascinating potential of the LLM. I would like to be able to speak to my French colleagues. I mean, 40% of sub-Saharan Africa speaks French. I mean, I'll be able to overcome the language barrier in doing business across that region. So there's a whole lot that you've communicated in this space. For us in this business, the goal is to be able to de-risk our opportunity effectively, whether you're in the business world or you are in the government regulation side. You want to be able to de-risk your opportunities, be able to finish your licensing round in a short term, or be able to get funding for your prospect or for the project that you're executing as an oil and gas entity. And that's what all these technologies will do, because being able to apply these technologies that you shared with us today will be maybe the determining thing for you to get funding or for you to move to the next steps in your project. And whether you're, for those of us who are still, who are actually employees, I mean, it's the skill set that will get you your next promotion. So thanks a lot again for this. We do really appreciate this and for helping us to bridge the gap between the traditional way of doing things in geosciences and what the future portends. So thank you very much again. Let's give him a round of applause for it. Thank you. We're quickly going to move into the questions. We've opened the floor to everyone. I will really recommend that we keep our questions concise so that we'll be able to engage with as many participants as possible. So please raise your hands or drop a chat. Drop your questions in the chat, and let's take full advantage of Rocky's presence in our midst. Thank you.
All right. So far we have a hand. Somebody we have a Motari Lawal. Motari Lawal, can you just go ahead? I'll unmute you. You go ahead and ask your question.
Okay, thank you very much for the opportunity. So I want to thank NAPI for this program. I just want to ask this question. For young or for students of geology, what's your advice for them? Where should they start from with regards to geology and machine learning? What should be the basic? Where should they begin? That's my question. Thank you very much.
That's a very good question. And I think, unlike myself, who is an old guy, we didn't have machine learning when I was in school. And things have evolved. The technology has evolved. You have grown up with it. If you're a student in university, and one of the things that I have learned in my career is as technologies evolve, people always question, well, the technology's evolved, it's going to put me out of a job. It always does the opposite. It produces more opportunities. I mean, think of what you can do with these machine learning applications. And I would encourage anybody coming out of the university or going into the university to be very much aware of the applications being used, AI and ML, whatever, and just be cognizant of what's going on. I mean, understand the basics. A lot of this stuff is not complicated. People make it sound complicated. Now, a lot of the computations are very, very involved, quite often hundreds of thousands to millions of computations. But in most cases for machine learning, those computations are not complex. Most of them are very quickly, they're easy, they're not detailed mathematical approaches. But if you understand the fundamentals, you understand the basics of what's going on, you can understand how they got that answer, or at least the method they got it, and make a intelligent scientific decision on whether it's accurate or not. So just be very much aware of every machine learning, artificial intelligence, data science course you can take them, because it is not only the future of geoscience and geology, it's the future of everything, I think, that we're in our society today. Hopefully that helped answer the question.
Sure,
Right.
sir. Thank you very much. It's really helped. I appreciate it.
Thank you.
All right. Thank you, Rocky. We have Dr. Ejenevi. Please, can you go ahead and ask your question, Dr. Ejenevi?
Okay, thank you, Mr. Rocky. It's a very good presentation. I'm prepared geoscience technology today and the future, and in the near future, because I was trying to ask the question on how can this technology aid in a seismic interpretation for or 3 to 4D, but I've gotten the answer. My only worry is that that is in the upstream. We have the technology already on board here, and if that is yes, it means that the commission will be in charge of the technology adaptation. I lower my hand because I've gotten an answer, but if there's anything close to the ministry downstream relating to this field or this topic rather, it will be very, very good if you can take an advantage of that. Thank you.
Okay, I wasn't quite sure what the question was, but I think one of the maybe what you were asking was we have to be careful in the answers we're getting when we use any sort of AI and ML. Is that the question you're asking there?
I think it was there was a reference to like midstream.
That more downstream.
Yeah.
Oh yes. In fact, I would argue that the application of the mid and more downstream, they're actually more advanced in the application of AI and ML than we are in the very upstream. Our very upstream, I hate to say it, but maybe it's my generation of geoscientists, are less accepting of new technology. I mean, it took 20 years for 3D surveys to take hold. I mean, we're not very, we don't move real quick when it comes to new technologies, but we have to now. Everything's there. But I again, the more midstream and especially downstream ends of our industry they've been doing a lot of machine learning applications and statistical sort of approaches for years, actually. They're more advanced than the very upstream part of the geoscience world. Thank you. That's a good question.
All right, Rocky. We have I think we have another question on the chat. They said, where does LLM play in all of this? Also, could vibe coding be helpful in reinforcing these advancements in geosciences?
I understood the large language model, but what was the last question?
Okay, so where does LLM play in all of this? Also, could vibe coding be helpful in reinforcing these advancements in geosciences?
Was that Python coding? Is that what the word, or just coding in general?
Vibe coding, when you make use of code libraries,
coding.
yes.
Yeah, that's what it is. Yeah, well, that is what's evolved in the world. And it's not just large language models, but that's one of them. But almost all these applications of machine learning that I showed you, you can almost get that on Python free. In Python codes to do this. And there's these LLMs you can get. I mean, they're in Windows, they're in Microsoft applications, they're in all of our, a lot of our everyday applications that we use today, are these large language model involved in doing these sorts of things. And that's where things are going. I mean, that's kind of the direction things are going. And some of the things I showed you is that we're starting to kind of spread out and do some very specific applications in geology and geophysics with a lot of these, the technology, or at least the architecture of large language models. But a lot of this you can get online free. You get these Python codes are free. And now you have to understand how to use them, but we're seeing a lot of evolution in a lot of these machine learning applications because people can start to use them online free. And not only that, some of these large language models will do it for you. You can tell it what to do, and it will take some of this free code and actually do whatever you're asking it to do. So that's kind of how things are evolving, and we'll see how it all happens in the end. But it's quite exciting, I think.
All right, thank you, Rocky. And so we'll take the last question, and the last question will be from the Abuja chapter coordinator, Dr. Eunice. Please, madam, you can go ahead and ask your question.
Dr. Ajayi, please go ahead.
Thank you so much. Okay. Thank you so much, Rocky, for that insightful presentation. I got this question from the question and answer panel, and it says, I'd like to know the fate/future of geoscientists in the AI evolution.
Well, that's a pretty big question. I think I'm extremely excited about it, to tell you the truth. The reason I say that is, as Akin indicated, I've been involved in machine learning for quite a while, more than 12, 15 years. And even way back before that, when some of the very earliest machine learning applications were used. But what I have seen is I've seen results and information that is telling us more about the Earth and geology than anything I could see before. I can see things, depending on what you're doing, in more detail and higher resolution than I've ever seen before. I've seen, there's things like the way that various depositional environments form, deep water, deltas, barrier bars. These things have very unique properties. Machine learning is starting to bring that out and looking at it with our seismic data. And I think we're just at the very edge of understanding that. And there's all kinds of things called self-organization, where which a lot of geology is self-organized. And a lot of our machine learning applications can bring some of this out. And so I'm extremely excited. I wish I was quite a bit younger, because I would really like to apply where things are going with the evolution of computer power and to see things in geology that I could never see before. So I'm really looking forward to the future, and those of you involved in it, I think it's extremely exciting. Thank you very much.
All right. Okay.
quick, thank you again, Rocky. That was outstanding, great answers, and I think you've really enriched the whole of the community. Everyone, like we promised, in a conversation with Rocky yesterday, we were talking about, I brought up some of the works that he's done is an aggregation which he's been involved in Roden and Associates. There's a DHI catalog that they've been working on for the last 25 years. And the catalog actually shows DHIs, which would be very useful for anyone that is looking for analogs and needs to maybe evaluate their DHI opportunities. We will be sharing the link to that, thanks to Rocky. So you'll be able to register and be able to register in that website and have access to the work that they've done for 25 years and over 400 DHI opportunities. Rocky, you want to say a word about that?
Yeah, I can. Yeah, thank you. We started about 25 years ago. We didn't think it would last but a couple of years, but what happened is we got a bunch of oil companies together and they started showing prospects, and we evaluated these prospects. They would show the technical evaluations. We would ask questions. We don't know the answer. And we would ask technical questions on data quality. How did you do this? Did you do that? Look at pre-stack data if we have it. And ultimately, we risk the prospect. And then the oil company representative who showed the prospect would give the answer. And so this methodology we started 25 years ago, and we built a database of over 400 prospects. We've had over 80, almost 90 companies involved in this for the 25 years. And it's been around the world, by the way. And this has been we've learned a significant amount of information on how to evaluate prospects. And I think in the future, as things evolve with AI and ML, we're going to get better and better. And one of the issues we're really seeing is how full waveform inversion is potentially impacting how we risk prospects where that has been acquired and processed. Because the images we're seeing now, especially subsalt, which we never in the past believed the amplitude subsalt, now we're starting to get subsalt amplitudes that are believable, and we've proven it by the wellbore in some cases. So it's getting better, and our technology is getting better. So thank you, Akeem.
Okay, thank you, everyone. Dr. Eunice. So that's that is actually the giveaway that I was talking about. It's a trove of information for community.
Quite amazing. Thank you so much, Dr. Rocky, for that insightful, awesome presentation. So I'd like to invite Dr. Maya for the presentation of award to our guest speaker. Dr. Maya, where are you?
All right, thank you. Permit me to share my screen. Okay. All right, please confirm you can see my screen.
It's coming up.
Okay. Is it up now?
No, it's not yet up.
Not yet.
Not yet.
There it is.
Yeah.
Okay. That's it.
All right. All right. So on behalf of the NAPI Abuja chapter, I am very honored to present this token of appreciation to Mr. Rocky Roden for his insightful and engaging presentation today at our second quarter technical meeting. Your contribution has added immense value to our discourse, and we sincerely thank you for sharing your expertise and your time with us, considering that we understand the huge time difference from where you are. Please accept this e-plaque as a symbol of gratitude and recognition. Once again, thank you, Mr. Rocky.
Thank you. I sure appreciate it.
Thank you, Mr. Rocky. I think we'll either mail it to you or probably when someone is coming to Nigeria, we'll find a way of getting it across to you in Texas. Thank you once again. Really appreciate your time.
Thank you.
And also your sacrifice. You've woken up since 6 a.m. or 5 a.m.
No problem.
It shows the love you have for us and the zeal to impart this knowledge to every one of us. We say thank you once again. So
thank you.
Over to you, Mr. Guno, for announcements of NAPI activities.
All right, thank you. Thank you very much, madam. At this point, we'll just go forward. We'll take the announcements. Can we have the announcement slides?
Should I share it?
Yes, please go ahead and share the announcement slides.
Can you see it?
Yes. All right. Thank you all for joining today's presentation, the technical meeting for Abuja. We just listened to the presentation on trends in geoscience technology today and in the near future, as presented by Rocky Roden. Next slide, please. And so just for us to know, that we have some upcoming technical presentation, and that will be from the Oka chapter, and there'll be the discourse will be on unlocking sweet spots using the reservoir geophysics techniques and strategy for well placement optimization. That will be for Thursday this week on the 15th of May 2005, and it's a virtual meeting, so we can all be part of it. You can join from wherever you are in the country or outside the country. And we also have one coming, the Lagos, the May technical meeting and technical and business meeting in Lagos. It's going to be, the discourse will be on optimizing the OBN seismic surveys, the insight from Agbami 4D Monitor 3 acquisition. Of course, it's going to be a hybrid session, both physical. The venue will be at the Echo Hotels and Suites, the ground ball hall. The speaker, it's Dr. Ayodering Ade Kenley. We also have, for those of us that will be outside Lagos, we also have the virtual link that you can also join and be part of this technical meeting. And this meeting was proudly sponsored by the Chevron Limited. And of course, as also part of the presentation, there will also be other panelists that would add value to the discourse for that day. On Wednesday 28th, we have the technical meeting from the North American chapter, and the discourse will be extending the frontiers of deep water exploration, and it will be presented by Professor Paul Mann. and it's also a virtual meeting. So this is just a call for the submission of research proposals, the NAPI 2025 research grants in aid. So if you are an active member of NAPI and you're carrying out research in any of the institutions, you kindly follow the guidelines and make your submission for the research proposals. Please, you can refer to the NAPI website and get more information on this. We also have the mentoring circle for early and mid-career it's an early and mid-career enhancement program. And you have the link to enroll as a mentee. There are very experienced and very fantastic mentors that have been been listed to mentor and to help young professionals, and also young professionals to become to share knowledge and also to be impacted with their wealth of experience. You can check on the NAPI website to get more information on this. Now, this is the basic and evaluation competition. The registration deadline is this week, this Friday, the 16th of May. So please enroll your university to be part of this competition. We're also announcing the 2025 NAPI election. So please, if you have nominations or you want to pick up forms to contest for the available position, please refer to the website and get more information on the NAPI election. All right, so this is just to announce the 43rd NAPI Annual International Conference and Exhibition, which is coming up from the 9th to 13th November 2025 at the Echo Hotel and Suites in Lagos. And this year's topic will be revitalizing the Nigerian petroleum exploration and production strategies for energy security and sustainable development. Please be part of it. We have the early bird registration. It's on, and it will last till the 1st of September. And after the 1st of September, of course, you will have a hike in the registration price and the registration fee. So please be part of it and plan towards this year's annual international conference in November. We're having a call for abstracts. So you have paper presentation, oral presentation towards this year's international conference. Please submit your abstracts. We have the deadline on the 31st of July 2005. The abstract submission will end. On the 31st of August, you will be issued your acceptance letter. And the 30th of September, the submission of all full papers and extended abstracts will end. And on the 30th of September, you also have the insurance of the letters for the judges and the chapter chair. We're all encouraged to be up to date in the payment of our dues. Please, you have all the information, or you can go to the NAPI website and get any information on how to be updated in your financial records. In celebration of NAPI's 50th anniversary, with the team pioneering the the future of energy in Africa. This event is coming up in August the 14th at the Echo Hotels and Suites. All right, thank you very much for staying up to this point and listening to the announcement. At this point, I would like to call on we have the NAPI President-elect, Mrs. Olajumoke. I would like to up to give us a vote of thanks, and after which the NAPI President will also give us a closing remark. Thank you very much.
Thank you very much. Thank you very much, Dr. Eunice, for the technical meeting of today. The topic is really an insightful one. I really enjoyed the presentation. You know, there can't be a better time than this to have such paper presented. Thank you very much. And to our speaker, Rocky, thanks for your time and thanks for the excellent presentation. From the questions asked, it shows how interactive the presentation was and how insightful it was. So we really appreciate you and waking at that early hour of the day to be with us till this very moment and putting up such a wonderful presentation. We appreciate you and we believe that when NAPI calls on you in future, you'll be readily available to honor our invitation. Thank you very much, Dr. Eunice. We appreciate you and your ESCOs for today's technical meeting. And the last one, was it in March? Your presentation in March too was really insightful. We thank you and all our fellows that are on this call. We thank you for your time and every other person who participated. So be rest assured that we'll always give your chapter the required support at every point in time. Thank you, everyone.
Thank you. Thank you so much. I think for the closing remark, I would like if Mr. Eyi to please close us at this moment. I think the president actually called in that he has an emergency meeting, and he would like someone else to take the closing remark for him on his behalf. VP, are you around?
Yeah, good afternoon.
Okay, good afternoon. Yeah, go
Okay,
ahead.
I thought the PE did the closing remarks.
What?
I said I thought the PE did the closing remarks.
She gave the vote of thanks. So you can
Oh,
give
vote of
thanks.
thanks. Okay, yes. Okay. It's been a very insightful presentation, and I mean, and it was quite engaging with the questions that were asked. I want to thank Abuja chapter for this presentation, and also the speaker, and also everyone who turned out, including the chairman of the occasion. So now this is what TAPE is all about. I will continue to give out this kind of presentation for our community. So it's been a good one. I want to say thank you to everyone. Have a good day.
I also want to thank Mrs. Folashade Oladipo for coming also. She's actually has spent 3 decades in the oil and gas sector, and she's actually today addressed the problem which no one has ever actually looked into, the safety moment for our well-being. Thank you, Ms. Folashade, and we look forward to having you around another day. Thank you. And to close all, I also want to appreciate that our chairman of the day, Mr. Akinola. Akinola, you've really been amazing. You've actually been following up this meeting from since February. That we're supposed to have had it in the first quarter, but it was shifted till today. And Mr. Akinola has actually been the one that facilitated this meeting, the guest speaker, Dr. Rocky to be available here today. So we thank you, Mr. Ladipo from, I know you're speaking from Texas, Houston, and you've been awake since 5 a.m. Thank you so much. We're looking forward to subsequent meetings, and I hope you're going to attend. So our next meeting is going to be in July, and we'll be sharing the contact with you, and we'll be so glad to have you attend the next meeting. Thank you very much, and God bless us all. Bye.
Thank you, everyone.
Okay. So, Mr. Tunde, closing. Let's work this, Mr.